Hello everyone. In my previous classes we have already discussed about the two types of transport coefficients, that is electrical conductivity and mobility. What is electrical conductivity? What is the meaning of mobility? Their corresponding equations, and also electrical conductivity in terms of mobility is already studied. So today we are going to study about the dependence of temperature on electrical conductivity as well as mobility. First, let us study about how electrical conductivity depends on temperature. That is, as the temperature is going on changing in a semiconductor, how the electrical conductivity will change. Let us study using the equation, and later on let us plot it graphically and draw some conclusions out of it. In semiconductors, the dependence of conductivity on temperature is often pronounced. So let us first consider the simplest type of semiconductor, that is a pure semiconductor, which means we are going to consider a semiconductor in intrinsic region. And also we have derived the conductivity formula in intrinsic region is sigma is equals to Ne into mu E plus mu H, where N is nothing but the carrier concentration, which is intrinsic, E is the charge of the electron, mu E is the mobility of electron, and mu H is the mobility of holes. Let us consider this as equation number 1. But in this equation we are not having any temperature term, so that we can directly link electrical conductivity with temperature. That's why we need to use other equations where we can link conductivity with respect to temperature. And already we have derived the carrier concentration equation for intrinsic region, which is nothing but N is equals to 2 times of kBT divided by 2 pi h cross square whole raised to 3 by 2 into Me into Mh whole raised to 3 by 4 into exponential of minus Eg by 2 kBT, where kB is nothing but the Boltzmann constant, T is the temperature, Me is the effective mass of electron, whereas Mh is with respect to holes, Eg is the energy gap, and T is temperature. So this is the equation which is nothing but intrinsic carrier concentration. So now if we just substitute this equation number 2 in our equation number 1, we can easily find out the relation between conductivity and that of temperature. So in place of N in equation number 1, we are substituting value of N from equation number 2. So we will get sigma is equals to 2 times of kBT by 2 pi h cross square whole raised to 3 by 2 into Me into Mh whole raised to 3 by 4 into E into mu E plus mu H into exponential of minus Eg by 2 kBT. Here we have two different terms which are explaining about temperature. One is T raised to 3 by 2 and another one is the exponential term. But already we have discussed that conductivity, or even if you consider the carrier concentration, the dominant term is the exponential term. So we are considering other terms as constant, and it is a function of temperature, but dominant term is the exponential term, and we can just say that sigma is equals to f of t into exponential of Eg by 2 kBT. And the point to remember is the electrical conductivity increases exponentially with temperature, because f of t function weakly depends on temperature. So if you plot a graph of electrical conductivity as a function of inverse of temperature, we can observe exponentially decreasing graph as shown, because sigma is directly proportional to E raised to minus Eg by 2 kBT. Here we are having the temperature 1 by T, so when you plot, it is minus of that term, so we get exponentially decreasing graph. Again, for simpler way in order to interpret the conclusion, let us take natural logarithm to this equation on both the sides. So what we get? Ln of sigma will be equal to ln of the whole term. It is something like ln of a into b, which will be equal to ln of a plus ln of b. So it is ln f of t plus of ln e raised to minus eg by 2 kbt, and ln of m raised to n is nothing but n into ln m. That's why we are having ln f of t minus the exponential term, that is eg by 2 kbt into ln e, and we know ln e is nothing but 1. So we are having a equation which is of the form y is equals to mx plus c, which is nothing but the equation of straight line. So if you plot a graph of ln sigma as a function of 1 by t, we get a straight line with an intercept because there is a function, there is a constant ln f of t, and the curve is having a negative slope, that is it is something like y is equals to c minus m into x. So if you take the slope of it, then the slope will be equal to eg by 2 kb, and minus represents it is a negative slope. So we are getting a decreasing straight line. So what is the use of it? If you just find out the electrical conductivity of a specimen, that is semiconductor, for different temperatures, easily you can plot this graph, and when you take the slope of it, that value has to be equated to Eg by 2 kb, and we know kb is nothing but the Boltzmann constant. So when you substitute these values, easily you can find out what is the energy gap of the given semiconductor. So this method was the old type of method of finding the energy gap of any semiconductor. But nowadays, generally we use optical methods to measure the energy gap, which will be again discussed in our coming classes, that is under fundamental absorption. So this is the use of understanding the dependence of electrical conductivity as a function of temperature. So if you have the slope, easily you can find out the characteristic parameter, which is nothing but the energy gap of semiconductor. And if we know the energy gap, easily we can say that this semiconductor is nothing but whichever element, whatever it is. Like if energy gap has come up to 1.1 electron volt, then directly we can say the specimen is nothing but silicon. So this is the conclusion or significance of this method. Then we have considered this for the intrinsic region only, but we use extrinsic semiconductors also, and for extrinsic semiconductors we have the contribution for sigma is equals to sigma E plus sigma H, that is conductivity due to electrons and conductivity due to holes. Here N is not equal to P, and we need to consider both the carrier concentrations, and the temperature dependence is not usually strong as in case of intrinsic. So whenever you are going to consider the temperature dependence, mainly you can observe the temperature dependence in intrinsic region when compared to extrinsic region. So for extrinsic region, the main factor which is going to decide the electrical conductivity is the impurity concentration and not the temperature. Temperature dependence will be there, but it is comparatively less when compared to the influence of concentration of impurities. And when you consider the intrinsic region or intrinsic semiconductors, the temperature dependence is very pronounced. So this is about the dependence of electrical conductivity on temperature. So in my next class, we will be discussing about the dependence of mobility on temperature. Thank you.